Okay, this video has two definitions and two theorems, but these are not theorems that I'm going to work out. They have discussions of them in the book. I won't call them exactly proofs, but they're really just thinking about the implications of what we've already done. So a matrix is said to be in reduced row echelon form. Some computer programs use this and they just call it RREF. If the following three conditions are satisfied: any row containing a non-zero entry precedes any row in which all entries are zero, if any. So if there's an all-zero row, it's at the bottom. The first non-zero entry in each row is the only non-zero entry in its column. So if there's a 1 there, that means everything below it is going to be 0. And that's true for all of my entries. The first non-zero entry in each row is 1, and it occurs in a column to the right of the first non-zero entry in the preceding row. So I could really have anything I wanted here. Like that could be a 2. That's not banned. But the first non-zero entry here is a 1, and it has to be to the right of this non-zero entry, right? And everything below it has to be that. This could be 0. Yeah, we've got that. And then we could have something like this, right? And then you could have something strange like another entry up here. And that is in reduced row echelon form. Now, the reduced row echelon form of a matrix is unique, and notice that Gaussian elimination we've talked about transforms any matrix into its reduced row echelon form. So if you look through the 7 steps in Gaussian elimination, this is algorithmically exactly what you do. You get that 1 as far up and as far left as you can, then you make everything below it 0, then you move to the next row and you move right, and it actually satisfies these. So you can think about that. There's a bit of a written discourse on it, but this theorem just observes that this is the construction that Gaussian elimination follows. Okay, so what is a general solution? Given a system of linear equations, a general solution is an equation describing all possible solutions to the system. So general solutions to a system, so that's the definition. And then sort of more precisely, when we're writing it down, we write them down like this. If the system is ax equals b with n variables and r non-zero equations, they're usually written like this, where s naught has to be a single solution, because the t's are variables that aren't restricted at all. So the t's could all be 0, which means that better be a solution, right? And u1 through u to the n, u sub n minus r, is a basis for the solution set of the homogeneous system of equations. And you can, that kind of makes sense if you think of this as being a single solution. If you subtracted a s naught from this side, well, that's equal to b. Then you subtract a s naught from this side equal to b, and you'd actually get the homogeneous system of equations there. That's formalized in theorem 3.5, which says let ax equals b be a system of a system with n variables and r non-zero equations. If the rank of a equals the rank of a augmented by b, that means your system can actually be solved, right? If that weren't true, then what you would have is you would have something like this, right? And there's no way to solve that last equation there, right? But if these ranks are the same, there aren't any non-zero rows over here, okay? And if a augmented by b is in reduced row echelon form, then because we have no non-zero equations, this says the rank of a actually is r, and the general solution is, as we discussed it above, with this as a basis for the homogeneous system of equations. Again, there's more discussion on that in the book, but this is important intuition because we're using this quite frequently to practically write out our solutions.